So let's call this. No, sorry, I chose the wrong there. Okay, so give me a second. Okay, so let's call this review. And what did that problem say? Let's see. So this was question 4, practice exam 1 or exam 2. Okay, let's see. So let me see if I can find it. Question 4. Okay, this is the one about the kite. Oh, yeah, this one was interesting. So let me see if let me write it here first. Of 30 feet. The kite string is being let out at a rate of 2 feet per second, assuming the string remains straight. What is the kite's velocity? Okay, so let's try to make a, again, in all these problems, word problems, typically you need a picture of the situation. Otherwise you'll get stuck pretty quickly. So you have a kite. Well, I'll draw the kite like a balloon. I don't know. So you have a kite, which is always at 30 feet. So the kite is moving this way. Oops, it's moving horizontally, right? So let's draw a picture for the floor, the ground level. Okay, so it always maintains a altitude of 30 feet. So you can put like a bunch of dots representing like the position of the kite at different times. But you see, it always remains like at an altitude of 30 feet. And so let's see. Yeah. What is it like, if you can imagine that there is like a kid with the string playing with a kite. So we can put like the string here. I mean, maybe there's like a fixed location where the kid is located. So like there's like the string here. Okay. And you see, like as the kite moves to the right, you need more and more string in order to keep the kite at a constant altitude, right? Because the kite is moving away from you. So here's where you have to be a little bit careful with the names that you give to things. We can call this L for length of the string. So what this problem is saying is that the LDT equals what? 2 feet per second. Is that making sense? Is this okay so far so good? Okay. Now, what is the problem asking for? The problem is asking for the kite's velocity, right? So the kite again is kind of moving this way. So what you can do is call this x, right? Like you can call the position of the kite from some point x. So the kite's velocity is the dt. Is that making sense? And so the key in this problem is just to realize that you have a right triangle here. Right, so 30 feet squared. So this is where you have to use Pythagoras theorem. Is that okay? And then, this is the key in all these problems about related rates or optimization. You always need to find like a variable or an equation that relates like the things that you care about. So we want the XCT, but we don't have that much information about the XCT, but we do have information about the LDT. So we have to relate somehow X with L. And so the easiest way to relate them is using Pythagoras theorem. And once you get there, like, then you can, like, the problem is a little bit more easy because you can take the derivative with respect to time on both sides of the equation. So, well, the first one is not 900, it doesn't matter too much. Because this will be a constant, so the value goes away. So the derivative of x squared with respect to t is 2x dx dt. And the derivative of L with respect to L squared with respect to t is 2L dL dt. Okay? And that, so that means that x dx dt equals L dL dt. But we have information about what the LDT is, right? That's 2 feet per second. Okay, so that gives you an equation for the xdt. The xdt is L over x times 2 feet per second. But we want this value when L is 50, the string is 50 feet out, 50 feet out of the string is out. So we want L to be 50. And what would be the value for x at this point? Well, you have to use Pythagoras theorem again, because from Pythagoras theorem, you have a 30 squared plus x squared, right? Is now 50 squared. And so if you solve for x, I believe you get like what, 40 feet. So x should be 40 feet here. So the dt is going to be L, which is 50 feet over 40 feet times 2 feet per second. Is that making sense? So this gives you 100 over. I mean, you can simplify this a little bit, I guess. But yeah, you can say 10 over 4 is 2.5, right? Is that making sense? So again, it's all for this related rates problems. It's always identify the variables, find the relationship between the variables, and then take derivatives to find the rate that you care about. Okay, so there's a question about doing the mean value theorem problem from midterm 3. So we can go to that one next, if that sounds good. So are there any questions with this one before I move to the mean value theorem problem? Okay, so let me go there to that one. Oh, did I post Okay, so by the way, I mean the solutions were I did post the solutions, but I just forgot to post them on the modules, but they are on their files. But then before I forget it, I'm going to put it now on their modules. Yeah, that was my mistake. So now if you go to the Canvas side and you click on modules, you will be able to find the solutions there. Is that I had not done that before, so sorry about that. I have the solutions for all of them written out. Yeah, no, I just think I don't know why I didn't put them on the module part, but now this is fine. I think. Yeah. And then for the first exam, I also cannot put them on the Canvas on the modules part. Okay, I think now it should be fine. But so now you can find the solution on the modules. Okay, so let me explain the mean value theorem problem. So it was that to show that for theorem less than x less than 1, you have this inequality. Okay, so let's see. So what happened here is like first you have to remember what the mean value theorem said. The mean value theorem said that if you have an interval, like if you're looking at a function on an interval a comma b, then there is a c. This is what the mean value theorem said. There is a c between a and b. for which f prime of c is f of b minus f of a divided by b minus a. Okay, so if you look at this, like it's saying that the derivative is kind of like equal to some ratio, like a ratio which is kind of the average change of the function over this interval. So if you compare, like, I was trying to put it in a way that kind of could be comparable to what we have here. So if you look at this, like the function appears in the numerator, and then the denominator, you just have the difference in the values of the interval. So what was a little bit, I think there was a similar problem on the practice exam. What you have to do here was kind of think of the interval as being 0x. So which is kind of what could give like a little bit of it was a kind of like the subtle part of this problem. So you can think of the function, like think of the function as being related to it has to come from the numerator somehow. So the idea was to take the function to be t plus 1 on the interval 0x. Because if you do that, then this is kind of like a and b. Then what does f of b minus f of a over b minus a becomes? F of b is like root of x plus 1 minus f of a is 0, so let me write it like this. It would be f of x minus f of 0 over x minus 0. That's what you get if you do the substitution. But what is f of x? F of x is root of x plus 1. What is f of 0? F of 0 is root of 1. And b minus a becomes, and x minus 0 becomes just x. So you get root of x plus 1 minus 1 over x, which matches what you see in the in this ratio. Is that making sense so far, so good? So like the trick was kind of to compare the expression of the mean value theorem, which is a ratio, right? So in the numerator, in this expression, the numerator should be related to the function, and the denominator should be related to the interval. Okay, but then what is the derivative of this function? The derivative of this function was the derivative of root of t plus 1. That's 1 over 2 root of t plus 1. Okay, so what the mean value theorem says is that there's like a value where f prime of c equals root of x plus 1 minus 1 over x. So this is 1 over 2 root of c plus 1 equals root of x plus 1 minus 1 over x. But the thing is that c is between 0 and x. And x is between, and x is less than 1. So, you know, 1 over 2 root of c plus 1 is going to be less than 1/2 because this number is slightly bigger than 1. Okay, and that's how you end up with this thing being less than 1/2. Is that okay? Are there any questions about this one? So, I mean, yeah, the key part here was kind of to identify the function from the ratio, the expression in the ratio. Well, okay, so here's the question. Why use the numerator only and not the denominator? Because if you look at the statement of the mean value theorem, the function, like in the mean value theorem, you're equating the derivative with a ratio, right? Here there's a ratio, but if you see like the function only appears in the numerator, if you look at this expression. So because it's always a change in the function divided by the length of the interval. So like the thing here was to realize that this x could be thought of as the length of the interval 0 to x. I think that's what many yeah, I think fraction of you took all of it to be the function. But it was, and like it's understandable because you see like an X at the bottom, but it was more to think about this X as coming from B minus A, not not as coming from like the function itself. So it's because like again, like just because the function only appears in the numerator of the expression in the mean value theorem. Otherwise, like the thing is like if you have taken, I mean, among other one of the things that happens if you have taken all of this to be the function, that has like a derivative that's more complicated and other things become worse. So yeah, the idea was to look at the numerator as providing the function, basically. Oh, well, there were other, I mean, it was more, the reason why this had to be, the things like in the mean value theorem, you see a difference of two numbers, right? You have a difference of two numbers, but here you only have a single number, right? But X is always, bigger than 0. So, it was kind of to like, let's see. What I'm trying to say is that it would have been maybe more clear if I had written like if I had written this like this, right? Then it looks more apparent because then you're thinking of this as you're thinking of this as a difference. Uh, and then you see, oh, this would be like the function that I'm plugging in, and this is what I get in this function when I plug in x equals 0. You see, it's just that secretly in the mean value theorem, like um, x, like if you have x at the bottom, you can think of that as x minus 0. I think there was another person who did it. Like, I mean, there were other ways to do it, but yeah, let's see. There was another way that someone had done it. If I remember. Yeah. Here's another way I think someone had done it. Another way. I think someone had defined f of t to be root of t. Okay. So here, what if you had taken the function to be root of t, what would be the interval that you need? What would that interval need to be? It would need to be the interval 1, comma 1 plus x, right? Uh, this would be like the A and this would be like the B. Because then f of B minus f of B, A over B minus A would be f of B, but B is f of 1 plus x minus f of 1 over 1 plus x minus 1, and that gives you root of x plus 1 minus root of 1 over x, and that gives you root of x plus 1 minus 1 over x. So yeah, it's not that the only choice had to be at the interval 0x. Another choice would have, for example, would have been this interval 1 to 1 plus x. The important thing was that the length of this interval continues to be x, which is the same as this interval. Because again, here, like in the mean value theorem, what you get is the length of the interval, right? Is that making sense? So the important thing was to choose like an interval whose length was the denominator. Like maybe I should write that down. So it's not that there was a unique option, but the important thing was to still think of the denominator as being like the interval, not the function. Is that making sense? Perfect. Anyone else? Which other one would you like me to go over? It can be about anything. Again. Also, I don't know if you saw the announcement I sent over the weekend. I figured that it made more sense to like do tomorrow's quiz as an assignment. So you can find it on the Canvas site currently. It's just two integral problems. So instead of having the quiz tomorrow, we'll just have that as, we'll just do this assignment as a replacement, because that way I can post the solutions to the assignment tomorrow as well. So you can have them earlier. I don't know if you have had a chance to look at it. Yeah, let's go over that one. Let me check that. Oh, okay. Yeah. So this is 8 from the review sheet for the final. So it was about find a function that satisfies. Okay, so this is like a typical integral problem because it's asking you to find like the function with a specific derivative, right? So here I'm giving you the derivative of the function and I'm asking you for the function, right? So we're trying to find so here I'm giving you the derivative and I want to know y of x. Here I know the derivative and want to find the function. So that is precisely what it means to find an antiderivative, right? So like what I'm trying to say is that like, the function should just be like the antiderivative of ln of x to the 4 over x dx. Is that making sense? Because this by definition is a function, oops, this by definition is a function whose derivative is ln of x to the 4 over x. Is that okay? So the question is, how do you integrate this function? So I use a small trick on the answers key of the PDF. If you saw the answer set that I wrote, I use a minor trick, but we can do it also without the trick. Let's see. Okay, yeah, we can do it without the trick, but it is a little bit more weird. So you have to. There's no way for us to integrate this without using a substitution. So the idea is like to remember that a logarithm has derivative 1 over x, right? So that's the thing that you have to take advantage of because 1 over x kind of appears here. So again, like if you want to read, if you read the solutions, you'll find a slightly different way to do this. But I'm going to do it like in a more with a slightly different flavor. So if you do it, if you just call u the numerator, what is du dx? It is 1 over x to the 4, right? Times, remember like what the chain rule says, you have to multiply by the derivative of the inside. So you have to multiply by the derivative of x to the 4. So that gives you 4x cubed over x to the 4, and that gives you 4 over x. Is that making sense? And so that means that du, if you multiply both sides by dx, is 4 over x dx. And so du over 4 is dx over x. Is that making sense? So the antiderivative, if you wanted to find this antiderivative, ln of x to the 4 is u, and dx over x is du over 4. Is that okay? And now this is an easy one to integrate. It's just u squared over 2. It's just that you have to write it in terms of x. So use ln square of x to the 4 plus c. Is that making sense? It's just now that you have to use you have to get rid of the constant, and then to get rid of the constant, you use the other information that y of e equals 1. So let me write this in a better way here. So now I want to use that y of e equals 1. So that means that one should be what I get if I plug in E here. Uh, so remember here you have to use the properties of log that you can take out the full move to the outside of the logarithm, the exponent. And ln of E is just one. So you get 4 squared, which is 16. Okay. So the answer is that okay? Is that making sense? Yeah, so again, if you read the solutions, I did it in a slightly different way, but you still need to do a substitution. So there's no way to get rid of a substitution. Uh, if that sounds good. Okay, so let's just do a quick 5-minute break. But in the meantime, if you want, keep thinking about what else you would like me to you would like to ask me, and then we can keep working on it, if that sounds good. So let's just do a 5-minute break quickly. But yeah, just take a look at what else you're confused about, and we can do more examples about it. Okay, let's see. Okay, I'm still sharing the tablet, right? So this is 12 on the review. This one is a nice one because it's just about the interpretation of the derivative. Oh, so I'm giving you the graph of a function, which looks like this. So, and I'm asking you to find, the problem asks you to find the, the definite integral from -4 to 4 of f of x here. Okay, so here is just one of these problems. I mean, one option would be to try to find like the formula for the function and try to integrate that. But I mean, typically in these problems, when you're given the graph, and if you look when the function has like a graph that looks either like lines or circles, the idea is more to use like the geometric interpretation because you can compute the areas of those things easily. So let me color a couple of things for you. I'll color this one. I'll color this one. Color this one. I'll color this one also. Let's see. And I'm coloring this one. Okay. So I'm breaking up the region into 5 pieces, and my claim is that on each of these 5 pieces, the area is easy to find. Okay. So let's start with area 1. What is the first area? So that's a circle. If you think about it, it is like a circle of radius 1, right? So what's the formula of a circle? It's pi r squared, right? Like the area of a circle is pi r squared. Oh, but over 2, because we're just looking at half the circle, right? It's half the pizza pie. So the radius is 1, so you get pi over 2. Is that making sense? Uh, you can kind of cheat a little bit, and like that should be the same answer for like area 5, right? Because area 5 is kind of found in the same way. So you get also pi over 2 as well. Is that okay? Uh, then comes area 3. What's area 3? Area 3 is like the area of a triangle, right? What's the area of a triangle? It's base times height over 2, right? So what's the base? The base is 1. The height is also 1, right? So you get 1 times 1 over 2. So that's 1/2. Is that making sense? Which is the same as, let's call that area 3. I forgot, sorry. Which is the same as area 4, right? Because area 4 is also a rectangle, sorry, a triangle with the same measure sides. And the last one, which we can call area 3, is the area of this rectangle. Sorry, I should have called, so this one, this was area 2, sorry. And area 3, which is this rectangle, is base times height over 2. Sorry, it's just base times height. The base is 2, the height is 1. So it's 2 times 1, which is 2. Is that okay of how I found each of these areas? And then the integral is the net area. So you just have to remember that it's all these areas with the appropriate signs. So the green one, because it's above the x-axis, is positive. The blue one, because it's below the x-axis, is negative. The red one is also negative because it's below the x-axis. The same goes for the brown one. And same goes for the yellow one. So you see, the ones with pi cancel out, and you just end up with -3. So the point here in this problem was to just distinguish between those which are positive area versus negative area. So there was only one that had positive area in this picture, which is the green one. Is that making sense? Good. Any other questions? Have you seen the problem? Okay, let's just go over the one that I posted for the assignment instead of tomorrow's quiz. I don't know if you have had like, a chance to check it out. So this is like the assignment for instead of quiz 10. Um, Okay, I don't know if you have seen this one, but it's a good one to check. It's one of the two problems. But if we if you haven't seen something like this before, it can be confusing. So it's just asking for the derivative with respect to time of dx over 1 plus x squared. Okay. So here you have to think about the fundamental theorem of calculus. So what the fundamental theorem of calculus says is that if you have, instead of having a t squared here, you would have a t So if there were only a t instead of a t squared, then the derivative, again, like the idea is that the derivative and the integral kind of cancel each other out. They're kind of like exponential and natural log or things like that. So whenever a derivative is an integral, they kill each other. Okay, so it's kind of they vanish together. So they disintegrate. So the rule is that you're just left with the function that's inside. But since the variable was t, the only thing that you have to do is replace the variable from x to t. So this is what the fundamental theorem says. So it's always the same. You cancel the two, you cancel the derivative with the integral, and just replace the variable in terms of the new one. Okay. Is that making sense? It's just the problem now is that we don't have t on the top. We have a t squared, right? The problem that we have now is that we have a t squared here. So we have to kind of treat this as a chain rule problem. What do I mean by chain rule? You kind of do the same strategy as usual, where you make a change of variables where u equals t squared. So this becomes the derivative with respect to t of 0 from to u of the x over 1 plus x squared. But now the problem is that these two do not match. These two variables do not match. So you cannot disintegrate them. You cannot cancel them yet. But then you do the chain rule trick of multiplying and dividing by du. Okay. And what happens now? These now they cancel one another because they have the same variable, and it's just like the variable is not raised to anything weird. So now these two cancel one another, and again, when you cancel, you get the same thing inside, but with new variables. And the new variable is now u. So this becomes in terms of u. So you get 1 over 1 plus u squared. Is that making sense? And you still get du dt here. Okay. Is that making sense? Are there any questions about this? But now you just remember that u was t squared. So you end up with 1 plus u squared is t to the 4. And what is the u dt is 2t. So the answer is 2t over 1 plus t to the 4. Is that okay? So again, in these change rule problems, I mean, in these problems where you have to take the derivative uh, with respect to t, if the upper bound is not just t, you have to make a change of variables first to put it in the right format. Oh, it's just like the thing is like here I was applying the chain rule, right? So I have to multiply by the chain rule, right? Like when you, to use a chain rule, you kind of divide and multiply by du. So you have the u dt. It's just that u was t squared, right? U was t squared. So the u dt becomes 2t. Is that making sense? So yeah, don't forget to multiply by the chain rule by the u dt. Is that okay? Are there any questions about this? Anyone, any other problem that you would like to go over? Uh, oh, this is another nice one, which is also on the review, but it's cute to see because it is like a fun combination of L'Hopital with this fundamental theorem of calculus. So it's kind of like a fun problem to look at. Um, so maybe let's do this one, which was a limit as h goes to 0. Uh, the integral from 0 to h of 1 minus cosine of x dx over h squared. Okay. So in this problem, there are actually two ways to do it. The longer way is to just try to do this integral first, to integrate that first to see what you get in terms of h, and then try to compute the limit. But the easiest thing to do is to try to kind of apply L'Hopital's theorem directly. Because remember, what happens if you put h equals 0 in this? What happens if you put h equals 0 here? You get the integral from 0 to 0, right? Over 0 squared. And no matter, this is important to remember, it doesn't matter what you have inside. If the integral goes from 0 to 0 of from one number to itself, right? There's no area it can enclose because like it's literally just like a line. There's no width of the interval. So there's no area here. So the integral from 0 from a number to itself, in any definite integral, that's always 0. So this one gives you 0. And so you get 0/0. And that's exactly the format that L'Hopital can help you with. Is that making sense? So this is already in the format of L'Hopital's theorem. So if you use L'Hopital, it is just the ratio of the derivatives, right? But the variable here is h, because that's like the limit you're taking with respect to. So you see, like, the thing is that to find this limit now, you can just use like the typical fundamental theorem of calculus. And the fundamental theorem of calculus just says that you can, oops, I forgot to write the limit. It says that you can just replace the x. It's the same thing that you have here. It's just like you replace x with the variable. And the derivative of the bottom is 2h. Okay, but again, if you see this again, it is 0/0. So this is 0/0 again. Is that making sense? Because like cosine of 0 is 1, so you get 1 minus 1, which is 0. So you can take L'Hopital one more time. What's the derivative of minus cosine is sine. And so this gives you 0. Is that making sense? So that limit is 0. And here you have to use L'Hopital twice. So this is like a fun example of how you can combine L'Hopital with these problems involving integrals. Is that okay? Is that making sense? Perfect. Any other questions? You can also ask it as a private message if you prefer not to write it down on the chat. But again, so as I was saying, I don't know if you had a chance. Let's discuss quickly the final exam. So I don't know if you had seen the Firefox site. So I posted here the guide for the final exam. So again, the exam is cumulative, so this guide only includes the new topic, like the summary of the new topics. And the new topics is basically everything that involves integrals. So you can check this guide, but you should also check the first 3 guides because in principle, like you can see problems that would have appeared in the first three exams. My plan was kind of to do 6 problems on integrals and then 2, 2, and 2. So like 2 from the first midterm, 2 from the second midterm, and 2 from the third midterm. That's kind of how I'm planning on breaking it down. So like 6 integral problems and 6 non-integral problems. And I will you will probably see I mean, you will see problems spread out from all the course material. So it is worth going over. My recommendation would be go over all the practice exams, go over the exams themselves. If you go over all of that, I think you will have like a solid number of problems to prepare yourself for. And then like for the new stuff, go over these problems and posted for the practice exam. Together with the examples we have been doing in class and things like that. So yeah, like what I was saying is that now you can find modules. I had posted them on the as a file, but not on the modules. So uh so let's see. Okay, so probably okay. At least we can definitely not to remove too much, but there are many limit problems from the beginning of the course that I wouldn't ask again because now you can just use L'Hopital. So it's kind of difficult to tell people not to uh, find a limit with a L'Hopital. Now everyone is kind of like, automatically going to go for L'Hopital. So if there's like a limit problem that I'm asking you to do would be with L'Hopital. So I won't say that it has Lopito in it, but like I'm just saying, like it will just be doable with Lopito. So in that sense, it you can like the earlier limits, like the way we were finding them with a bunch of tricks, you can probably, if you know how to do them with Lopito, then you're good to go because I won't force like a specific way to do them. Um, and so like in the first, like there are fewer things from the first midterm that I would add because if you remember, like the first midterm was almost was mostly limits. So many of them they just become super easy with L'Hopital. So yeah, I would say that something that you don't have to worry about. And then and yeah, like I guess like there was this quiz theorem on the first midterm. I don't know if you remember that squeeze theorem, but yeah, I like that one. Since it's a limit thing, let's say that yeah, you also don't have to worry about that as well, nor like these problems about finding the derivative using the limit definition. That's kind of one thing that we did I think it was on the second midterm, but it's not. I mean, again, the point now is just to find everything with all the tools we have discussed. So it doesn't make a lot of sense to keep asking to find derivatives with the limit definition if now you can find them in ways that are a lot easier. So yeah, basically I would say most of the limit things from the beginning of the course, I wouldn't add them in the same way because it no longer makes sense because now we have more tools to do them. But things like almost everything else, like these things with max and mean or like optimization, curve sketching that we did on the previous exam, that you can still see. Like what else? Like the chain rule problems, of course, implicit differentiation. Yes, that's good. But it's mostly like it's kind of more about that stuff. So there's not too much of the first midterm you have to worry about because it has been included in the new stuff. But definitely you pay attention to L'Hopital, that's important. The chain rule is important. And like yeah, this stuff about like applications of the derivative work like optimization, the related rate, things like that. Again, if I put a problem of that, I wouldn't put that it's not that I would repeat the second exam or the third exam on the final, but you may see like like as I'm saying, like one or two from each midterm of the previous midterm material probably you'll see, but yeah, I wouldn't worry too much about these limit problems. I won't ask them in the same way. L'Hopital for sure, but not like the older stuff with limits. Um, so well, I'm not like yes and no, in the sense like it depends on uh like I wouldn't change like the curve. I wouldn't change the grade on the exams, like the numerical grade. I would just change where an A begins or where B starts or C starts or things like that. Um, so it's more, yeah, it can be curved if needed, but not in the sense like of effect of changing the numerical scores. Only like that what it takes to be a cutoff. If that makes sense. So the course grade, like it is curved, kind of, but more like for where the letter grades start. If it's necessary, yeah, it would. Uh, but but it is an option. But the curve only is to curve for students' benefits. So it's not a curve to kind of shrink the margins, if that makes any sense. More like, oh, well, if you don't end up doing as well on the final as one would like, then yeah, I would just like curve it. Uh, Again, in this sense of like just making it easier for like getting it, yeah, making wider the margins for one an A or B or C. Is that making sense? I mean, also, like if you look when I had posted the announcements for the letter grades, like usually the letter grades I have been basing them on your exam scores, but obviously I will also take into account the classwork and other things for the course grade. So like usually the rule of thumb like is kind of I kind of construct the classwork so that it like never hurts anyone. So like the classwork typically will help everyone in the sense like if just based on the exams you had like a B, maybe thanks to the classwork you'll end up with either a B or a B plus, but you wouldn't drop to C plus. I wouldn't use the classwork to drop someone's grade. That's what I'm trying to say. I would just use the classwork like, oh, okay, this person was doing very well, did all the homework problems and things like that, and so uh yeah. So like what I would say to everyone is that probably your course grade at the moment is either your exam grade or like the letter grade that you would get from based on this exam things that have been posted on the announcements, or maybe a bit higher because of the classwork stuff. So, uh, but yeah, overall, I think you're doing pretty well as a group. So, hopefully the exam will go well. But we still have all of Tuesday and all of Wednesday to keep doing problems. I guess it's more like try. I don't know. I mean, I'm sure like you are doing other things throughout during the summer, but maybe or you're taking a second class or doing some summer jobs. But just try to go over, just check the practice exams I have been posting and all this stuff. Check if you have any questions, and we can keep discussing them tomorrow and on Wednesday. That sounds good. Um, but yeah, if you do all of that, I do think you'll do well on the final. So yeah, I think that's a good place to just go over all of this, and we can do whatever you want to go over tomorrow as well. So we can continue reviewing all stuff and things like that. Okay, okay, good. See you, see you. Bye, bye.